All right, hi all. So today we want to move on to the kind of second half of our vector calculus unit, and to do that we need a bit of an interlude. Now, as always, I always like to say the prereq to doing line integrals and to doing Green's theorem and all of that is, of course, learning about parametric equations and learning about vector functions. So a parametric equation is a curve or a set of equations that can model a curve. So what you take in is you take in some input t, and then you get two functions. You get x of t, and that gives you your x coordinate, and then you get y of t, and that gives you your y coordinate. And what you can do with this is you can model where x and y go as a function of t, and that obviously manifests on the coordinate plane. That gives a lot of pretty curves. And we determined how we could do line integrals over those pretty curves as well. We also discovered the notion of a vector function and then a vector field. Obviously, that's kind of an extension of parametric equations. Instead of, essentially what you do is you take in t and then you get your output as a vector. So you get x of t and you get y of t. And that obviously manifests itself on the coordinate plane as well. And it gives us a lot of nice applications to physics, of course. So now the job is to bump this up one level farther. And instead of talking about a curve that can be modeled with a parametric equation, we're talking about a surface that could be modeled by a set of parametric equations. So essentially what we're going to do is we are going to have a parametric equation modeling x, a parametric equation modeling y, or a parametric equation modeling z. There's no particular reason I've chosen x, y, and z. I could have alternatively chosen r theta phi or r theta z as well, or any other sort of coordinate system you'd like to use, double spherical, elliptical, whichever have you. We only deal with Cartesian, cylindrical, and spherical in this course. But what we want to do now is, of course, bump this up to the multidimensional case. Now, let's just start off with the definition, and we'll run through a couple of easy examples. We won't actually be doing any calculus today. We're just going to be kind of building intuition. Now, we basically say that x, or that a vector function r, is modeled by a series of equations, x of u and v, y of u and v, and z of u and v on some domain D. Now, what do I mean by this? Now, what this means is that at each point in the domain D, this is my domain D, and this is the u-axis, and this is the v-axis. And essentially what we do is we take in some point, we have functions for x, y, and z. Essentially, at this u and v, at this point u naught, v naught, I go to some x naught. An x function takes me to an x naught, y function takes me to a y naught, and a z function takes me to a z naught. What I then do is I then take this and I project this onto the 3D coordinate space. So here's my x naught, here's my y naught, here's my z naught, and I get a point, x naught, y naught, z naught. And then this is my vector r naught. Now essentially what happens at this point is you get a whole slew of functions by going across this whole domain. By going across this whole domain, you will end up getting u and v at all different points on the domain, and you'll be getting x, y, and z from each of those u and v. What you'll get is you'll get a surface that can be modeled parametrically. So on the face of this seems interesting, right? We can now model surfaces with parametric equations. That's pretty neat. What does it give us? So first, what we can do with it is we can find the area of this surface. So kind of similar to how we had the arc length formula, we could do the integral from a to b dt of 1 plus f prime squared, and then that gave us the arc length. What we can do is we can expand this to find the surface area of a multivariable function. And then what we can do is we can actually consider vector fields and consider how much flux is going through any point on a surface. But that's kind of the analog of the line integral, and for that we need a couple of more nuanced theorems for curls and divergences, which we talked about earlier. Let's talk about an example first. Don't mind the photo just yet. but I would like us to construct a surface generated by the following. The vector function r is given by 2 cosine u, v, and 2 sine of u. Okay, now what this really is this is a set of parametric equations that we need to deal with. It turns out what's interesting is that y of v is equal to v, or y is equal to v. So we could alternatively say that this that r is now a function of u and y, because y is now interchangeable with v, because this is single valued right there. But what can we do with the other part? We have a 2 cosine u and we have a 2 sine of u. Well, any pre-calc student would tell you that what you're going to do with that is you're going to square them and take the sum. Therefore, you have x squared plus z squared, because 2 cosine of u is x, to 2 sine of u is z. Can square them. You get 4 cosine squared of u plus 4 sine squared of u. It's equal to 4. Do you know why it's equal to 4? Well, because cosine squared of u plus sine squared of u is equal to 1. So you just can pull out the 4, and that would make sense. So what you have here is you have essentially that x squared plus z squared is equal to 4. And y is just equal to y, so the vector just really goes out horizontally in the y direction, and then it goes around in a circle, giving us a nice cylinder. And this cylinder goes around however far we want, and what you could do is you could restrict u and v in order to give a shortened amount of sphere, in order to give kind of a little arc of a sphere, or sorry, not a sphere, a cylinder, a certain length of the cylinder, or a certain arc of the cylinder. And of course, this here poking out is the y-axis. So I hope that makes sense. That's kind of how we generate going from a vector function over to a parametric equation that we can model by eliminating the parameters, really. That's what we're doing. Let's do another example. Let's determine a vector representation of the function f of xy, or z, equals 2 times the square root of x squared plus y squared. Now what I see here is I see z equal to being proportional to the radical of x squared plus y squared. What that immediately should do is start alarm bells ringing that we're going to be dealing with a polar, or a cylindrical or a spherical graph. Turns out this is actually part of a cone. But we didn't need to know that. What we can just do is we can set x equal to x, and we can set y equal to y. We can set z equal to 2 plus the square root of x squared plus y squared. This is what I would call the naive approach to this. I mean, it's sort of trivial that, of course, we could do this, right? But it does work. The other representation that might be a little bit nicer, you wouldn't want to deal with this when you're dealing with integrals if you ever needed to integrate this sort of parametric surface. But what you could do instead is you could go to a polar representation. Now, of course, again, this gives the following vector function. The other way we could do this is you could recognize that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And z is equal to 2 times the square root of x squared plus y squared, but we define that r squared equals x squared plus y squared. So therefore, we can say that z is equal to 2 times r. Okay? So now we have a r theta parameterization for this. So we can say that r of r and theta is equal to r cosine theta, r sine theta, and 2r. Okay, that also makes things pretty simple. Again, if you need to integrate this, this would be a lot easier dealing with trig functions as opposed to dealing with radicals where you might need a trig sub. Anyways, let's continue on to another example. For this one, I would like to consider a parametric representation of a sphere. So what we can do is we can dig back to the last unit when we discussed spherical coordinates. That's obviously the one that we would try to choose. You could choose the UV parameterization for a sphere, but that is quite ugly and probably wouldn't want to deal with that many square roots. We'll use the spherical case. We know that x squared plus y squared plus z squared is equal to a squared. That is the definition of a sphere. And we can also write x equals a sine phi cosine theta, y equals a sine phi sine theta, and z equals a times the cosine of phi. So now what we have here is a nice parameterization that we can turn into a vector function. So therefore, we can set r of phi and theta equal to a sine theta cosine or a sine phi cosine theta, a sine phi sine theta, and a cosine phi. Now, if we look at the unit sphere, we can kind of derive this ourselves. But just to make sure that we know which angle is which, we know that z is equal to the a cosine of phi. So here's my horrible drawing of a sphere. And we know that z is equal to a cosine phi. So if I have the point z here, I know that cosine of phi is equal to z. So this length is equal to a times the cosine of phi. Therefore, phi must be this angle. We call that the azimuthal angle. I don't really know how to pronounce that, azimuthal or something like that. And then that obviously means that theta is the polar angle that sweeps out the polar axis for us. So what we can do here is we can say, well, A is obviously not going to be domain restricted because it obviously goes from 0 to A, or, well, in our case, actually, R is not going to be a variable because we're dealing with a sphere of constant radius. So this is like a spherical surface, right? So this would be important for Gauss's law. Say if you had like a charge in here and you need to integrate an electric field across the surface of a sphere, or fluid leaving a spherical surface. Anyways, that's kind of getting ahead of ourselves. But what we can do is we can set domain restrictions. So what we have is that it looks like phi in order to get like theta in order to get a full sweep would be 2 pi. So theta is going to be between 0 and 2 pi. So we'll write that theta is in 0 to 2 pi. And then we can also say phi, well, it looks like phi would need to sweep out kind of the all of the vertical here. So phi would go to from 0 to pi. So phi is in 0 to pi. Now what this does is quite interesting. We can actually project this as a domain on the theta phi plane. So if we have theta here and we have phi here, we can actually represent this as some sort of rectangle, which is kind of neat to think about. So here we have 2 pi, here we have phi, and that's a rectangle. This is kind of what you would be picking your domain from, and then spitting it back into your functions to get the spherical representation. Anyways, that is what I have here. So thanks for watching. We'll see you guys in the next video.